Amazing things that we could never have imagined will be revealed to us. Is this the kind of team where everything seems possible? We are going to discover incredible things that we never imagined. And isn't that typical of this team where the impossible becomes possible? People have often questioned whether they are the only species in the wide cosmos. We have explored the possibility of life beyond our little blue planet, stared at the sky, and thought about far-off galaxies. At last, that possibility has materialized. The head of NASA recently said that something remarkable has been captured by the James Webb Space Telescope, our window to the universe. Prepare yourself, as an incredible secret has been revealed on the outskirts of our cosmic neighborhood. The discovery of life on the planet Proxima B alters everything. Come along as we explore the mysteries revealed by the James Webb Space Telescope and speculate on the potential implications of the finding of life on Proxima B for both humankind as a whole and space exploration in general. A scientific marvel, the James Webb Space Telescope has the potential to completely change our understanding of the cosmos. Thanks to the telescope's advanced technology and special location in space, scientists can now study distant galaxies, planets, and stars in a way that has never been possible before, giving them an unparalleled perspective of the universe. Although all of this sounds like a bunch of hokey assertions, the technology actually supports all of that. The 6.5-meter diameter primary mirror of the JWST is one of its most amazing features. This is more than twice as large as the primary mirror on the Hubble Space Telescope, one of the most significant space exploration instruments of the last 30 years. The JWST's massive mirror allows it to catch even the smallest light glimmers from the farthest reaches of the universe, regions that science hasn't always been able to observe. Therefore, most of the time throughout history, scientists have just made theories about what is possible to see using a conventional telescope. However, with this one, they can at last see the actual detail of which they had been daydreaming. The JWST has a big mirror in addition to a collection of cutting-edge instruments that can detect a broad spectrum of light wavelengths. The telescope's near-infrared camera, or NIR-CAM as it's commonly known, is a potent instrument made to take pictures in the near-infrared portion of the electromagnetic spectrum. Why does this matter? Well, we can go farther into the depths of the cosmos because near-infrared light can pass through dust clouds that block out visible light. Astronomers can see the birth of stars and galaxies up close, thanks to NIRCam's high-resolution imaging capabilities. The main goals of this specific equipment are to research the early cosmos and its first light, look into the origin and evolution of galaxies, and find and describe exoplanets previously unreachable by telescopes. Hidden intricacies and structures are revealed in the detailed photos taken by NIR-CAM. Understanding the assembly and evolution of galaxies throughout time is aided by this, and it provides insights into the intricate processes that form our cosmic neighborhood and beyond. However, that is only one tool. The near-infrared spectrograph, NIR-SPEC, is another option. Through the process of dissecting the light emitted by astronomical objects into its constituent colors or wavelengths, it raises the bar for the study of stars and galaxies. This procedure, known as spectroscopy, provides important details regarding the temperature, velocity, and chemical makeup of these objects. NIR-SPEC provides scientists with detailed information about everything it looks at, thanks to its capacity to study the spectral signatures of stars and galaxies. By analyzing the spectra's absorption and emission lines, scientists can identify the components of a star or galaxy and learn more about the materials that make up the universe. This knowledge aids in our comprehension of the complex interactions that occur between stars and galaxies, as well as the life cycles of these celestial bodies. Furthermore, NIR-SPEC is essential for studying distant high-redshift galaxies. These galaxies give forth light that has come to us after traveling over billions of years, giving us an insight into the early universe. Astronomers may determine a galaxy's age, chemical makeup, and other properties by analyzing its spectrum, which provides insight into the galaxy's whole evolutionary history. Throughout cosmic history, the mid-infrared instrument MIRI on the JWST is the main instrument for researching the mid-infrared portion of the electromagnetic spectrum. With MIRI, we can study objects that produce infrared light at longer wavelengths, which allows us to investigate a variety of phenomena ranging from star formation to the discovery of exoplanet atmospheres. Inquiring into the dusty environments where stars are created is one of MIRI's main objectives. These thick dust clouds are permeable to infrared radiation, which enables MIRI to look through the cosmic veil and observe the formation of stars and planetary systems. Astronomers may learn a great deal about the physical processes taking place inside the celestial incubators, thanks to the detailed photos and spectra it takes in the mid-infrared. That's not all, though. In addition, MIRI is essential to the identification and study of exoplanets. In order to enable MIRI to identify and examine the faint thermal emissions from exoplanet atmospheres, it accomplishes this by making mid-infrared observations. The composition, temperature, and motion of exoplanets, as well as their possible habitability, may be studied thanks to this capability. We can identify the presence of water vapor, carbon dioxide, and other essential chemicals, thanks to MIRI's discoveries, which may point to the prerequisites for life as we know it. However, those are merely elements that might sustain life. How does the James Webb Telescope look for biological indicators? Spectroscopy and atmospheric analysis, which make use of the four instruments we just discussed, are two of its primary methods. You see, a planet may not have had plants or oxygen from the beginning. Even while those indicate life to us, science does not believe that to be the foundation of life on a planet. Thus, the telescope needs to become extremely precise. Spectroscopy, a method that lets scientists examine light emitted or absorbed by an object to ascertain its composition, is at the core of this procedure. Spectroscopy plays a crucial role in revealing the molecular mysteries concealed in the atmospheres of exoplanets. When the JWST finds an exoplanet, it looks forward to a transit event, which is a celestial display in which the exoplanet appears to us as it passes in front of its home star. During this transit, the JWST closely monitors the starlight passing through the planet's atmosphere with its state-of-the-art instruments. The JWST records this priceless light while MIRI dominates the mid-infrared spectrum and NIRSpec focuses on the near-infrared. When combined, they create an unbeatable team that can cover a broad variety of wavelengths needed for in-depth investigation. What exactly is the significance of collecting starlight during a transit? One may wonder. Indeed, this starlight contains important information on the makeup of the exoplanet's atmosphere. Light interacts with different chemicals in the exoplanet's atmosphere as it travels through it, leaving behind telltale signs, like molecular fingerprints, left on the cosmic canvas. After that, the JWST begins its painstaking analysis of the light it has seen. By analyzing the absorption or emission lines in the light spectrum, scientists can use the telescope's spectroscopic capabilities to pinpoint particular compounds that are present in the exoplanet's atmosphere. Since every molecule has a different set of spectral characteristics, no two molecules will be the same. To bring the entire tale to a single coherent page, they simply need to be examined and assembled in order to obtain precise findings. The JWST does comprehensive modeling and calibration. It matches the observed spectrum features with their corresponding chemical identities using complex computer simulations and reference spectra of known substances. Consider it as a kind of cross-referencing an astronomical dictionary to understand the atmospheric language of the exoplanet. However, identifying particular compounds is only the first step in the search for life. A more all-encompassing strategy is needed. Researchers look for molecules that are regarded as biomarkers or compounds that might be connected to life as we know it. As we've mentioned previously, these biomarkers may consist of gases that are necessary for life on Earth to exist, such as oxygen, methane, and water vapor. Even so, more information and observations are required to evaluate the general habitability and any relevant biological activity indicators. Comparative spectroscopy is another tool that the JWST uses to improve its hunt for life. To draw meaningful comparisons, scientists examine a few exoplanets with comparable properties rather than a large number of isolated exoplanets. Finding recurring trends or aberrations in the observed spectra of various exoplanets is the goal of comparative spectroscopy. Examining a range of exoplanets, some of which may be habitable while others may not, allows us to look for patterns or anomalies that could shed light on the existence of molecules or processes relevant to life. The JWST searches for exoplanets that are comparable to each other in terms of size, mass, distance from their host star, and other pertinent variables in order to do comparative spectroscopy. In this manner, researchers can separate out the impacts of different atmospheric components and concentrate on possible habitability indicators. Scientists can search for similarities or differences in the detected chemical absorption or emission lines by comparing the spectral data collected from these target exoplanets. It may be a sign that essential components of life, such as oxygen, methane, or water vapor, are present on potentially habitable exoplanets. If specific compounds or patterns are regularly observed in their spectra, the context that the comparison technique offers is quite helpful in understanding the spectroscopic data. It enables researchers to discern between characteristics that are more likely to be linked to life and those that could be attributed to non-biological phenomena, such as volcanic activity or atmospheric chemistry. This is due to the fact that, despite appearing to be limited to Earth, phenomena such as volcanic activity actually occur across space. Even though some planets are entirely inhospitable, they nevertheless experience extremely high levels of volcanic activity. Furthermore, scientists might find abnormalities or unexpected variations in the spectra using comparative spectroscopy. These aberrations could represent distinctive features of a particular exoplanet, suggesting the existence of peculiar atmospheric conditions, or perhaps alien life forms that contradict existing theories. It's similar to discovering cosmic surprises and going beyond the realm of what we previously believed was feasible. A more comprehensive understanding of the habitability of exoplanets overall is also offered by comparative spectroscopy. Scientists can learn more about the various aspects that lead to habitability by studying a wide variety of exoplanets. It aids in our comprehension of the prerequisites for the origin and maintenance of life in a variety of cosmic settings. As per the NASA chief, Proxima B, which is only 4.24 light-years distant from our solar system and has gained significant attention due to its possible habitability, may have had life discovered there by the James Webb Telescope. Proxima B revolves around Proxima Centauri, the parent star of Proxima B, a red dwarf that is still significantly smaller and colder than our Sun. This exoplanet was found in 2016 and is situated in the Goldilocks zone, the star's habitable zone. The area surrounding a star known as the habitable zone is where conditions would be ideal for liquid water to exist on a planet's surface, which is essential for life as we know it. The finding of life on Proxima B is revolutionary because of its closeness to Earth and placement in the habitable zone. Proxima B's potential to support life has generated a great deal of attention and conjecture. It's crucial to remember that an exoplanet's habitability is a complicated puzzle with many variables to take into account. With a mass of around 1.3 times that of Earth, Proxima B is categorized as an exoplanet similar to Earth. It takes roughly 11.2 Earth days to complete one orbit around Proxima Centauri, according to its orbital period. However, things are more complicated than they seem at first. It doesn't follow that the planet will be an identical duplicate of Earth, and that anyone can easily migrate there. Because it orbits a red dwarf star and is roughly the size of Earth, there are multiple criteria that determine Proxima B's habitability. The planet's atmosphere is one important factor. In addition to serving as a barrier against harm, atmospheres are essential for maintaining life and controlling temperature. Still unclear is the precise makeup of Proxima B's atmosphere, which makes it difficult to make a firm determination about its habitability. Researchers are using the James Webb Space Telescope, among other tools, to investigate Proxima B's atmosphere. They will be able to investigate the light that transits through the exoplanet's atmosphere as a result. By examining the spectrum fingerprints, scientists can search for compounds that might be biomarkers, signatures that point to the existence of life. The existence of water is another aspect that influences habitability. Proxima B is in the habitable zone, but whether or not it has enough water on it to qualify as a planet need yet be determined. One important component of the puzzle is water. Whether it takes the shape of lakes, rivers, or oceans, scientists search for evidence of liquid water on the planet's surface. Since the presence of water is necessary to sustain biological processes and is frequently seen as a major indicator of habitability, they also take into account the presence of water in other states, such as ice or vapor. Proxima B's tidally locked state also begs concerns about its possible habitability and environment. In order to determine whether Proxima B's temperature is suitable for supporting life, scientists must also look into elements like pressure, temperature, and geological activity. Life can be challenging under extreme weather situations such as intense heat or freezing cold. Additionally, stability is essential since habitability might be disrupted by regular seismic activity or volcanic eruptions. However, not all stability is advantageous. It is thought that Proxima B is tidally locked, meaning that one side of the planet is always illuminated by the star, while the other is constantly dark. The enormous differences in temperature and atmospheric dynamics that could arise from the sharp contrast between the continually bright and eternally darkened sides could have an impact on the planet's habitability. Another important factor in the hunt for livable planets is chemistry. Scientists examine the planet's chemical makeup in an effort to find organic compounds, amino acids, and other chemicals that serve as the foundation for life. Scientists finally think about energy sources. Just like we need our daily dose of caffeine, life requires an energy boost. They are investigating if the planet's biological processes are sufficiently powered by energy from its star or other sources. The cosmic machinery of life is propelled by energy, which allows living things to proliferate, expand, and flourish. But does Proxima B truly meet the requirements to be referred to as a planet supporting life? Is there actual evidence for it? The actual finding of Proxima B was an amazing accomplishment. Proxima Centauri is our nearest star neighbor. In 2016, astronomers using the high-accuracy radial velocity planet searcher HARPS equipment found the faint gravitational tug of an exoplanet around it. The very accurate spectrograph known as HARPS was created expressly to find exoplanets, operating out of Chile's Las Islas Observatory. According to experts, Proxima B has long been recognized as a potential candidate for supporting life. Thanks to its location in the habitable zone, scientists believed it had the ideal conditions for liquid water to exist on its surface. But after this groundbreaking revelation, it now seems that Proxima B might not be just a potential candidate anymore. If the JWST's discoveries are correct, it seems that life may indeed exist there, and humanity's cosmic perspective is about to shift forever. This groundbreaking discovery of Proxima B's possible life-changing information not only opens the door to the notion of interstellar life, but also highlights the far-reaching impact of space exploration and humanity's long-standing fascination with the stars. It's only the beginning of what might be an exciting new era of astronomical exploration. The road ahead is unknown, but one thing is certain. The James Webb Space Telescope has just given us a glimpse into a universe brimming with possibility and wonder. And who knows? We might be closer to finding the answers to the most profound questions about life beyond Earth than we ever imagined.